All right, again, this is Mike Mazzarese. Thank you all for attending today's presentation. So it's a joint presentation today between Aestus, our guest speaker, and AST. I'll be covering the back end of the hour. And so first up is Todd Hallahan with Aestus, and I'll let him talk about his company a little bit once he gets going here. But Dr. Hallahan is the interim department head and the Sun Chair of Hydrogeology at Oklahoma State University, and Chief Technical Officer for ASTIS. So Todd, I'll go ahead and hand it off to you here in a second. Uh, we're all pros with these formats now. Send questions in through the Q&A. We'll go ahead and handle those at the end. So it's split about 50-50. So you'll have maybe about a minute in between the presentations once as we transition speakers to throw your questions into the Q&A for Todd, and then we'll go ahead and open it up at the end and get through as many of those as we can. So Todd, thank you very much for presenting today, and I'll hand it over to you.
Thanks. So as he said, I'm at Oklahoma State, and I'm also at Aestus, so I've got a managed conflict of interest. If you got questions about that, just let me know as to how that all works. But I've been doing this about 25 years, so I think we've sorted a lot of things out. So we're going to talk about remedial design characterization and thinking about doing that the way that medical doctors or the oil industry would, and some parts about that process that are not immediately clear. So we're going to talk a little bit about where we started and what electrical hydrogeology is. We're going to look at a BTEX case at a refinery at about 500 feet down. I took out an urban solvent site, so if you want to find out about that, let me know, but I wanted to make sure I didn't go over and I make sure I have enough detail on these sites. We're going to talk a little bit about BTEX and Carson. We're going to talk a little bit about an injection site relative to thinking about permanent monitoring. And so we're going to think about the sites that you normally think about in an electrical perspective instead of in a chemical or physical perspective. We started out with consultants and academics quite a while ago now, and we wanted to find a better way to characterize sites. And so we looked at the other industries as how they do things, and they scan things first, and then they go in invasively. And basically, people are still to this day running around with a drill rig and poking holes and hoping things get better. We developed a process that gets us to much better conceptual site models, and what that leads to is you can remediate much faster because you know what's happening in the subsurface, and we save our clients millions of dollars when we try to do that for them and sort out better ways to do these things. Worldwide, we've worked in a whole bunch of different places, and a lot of focus in the US, but we've done hundreds of projects to test out this process and work on how to do this best. Safety has been part of our perspective. We were started out with both engineers and geoscientists. Big focus on protocols and making sure we're doing things right, both from a QA/QC perspective, but also from a safety perspective. So no accidents since we started. We've got, with the ties to the university, we've got case studies, but we have peer-reviewed papers if you want to look at various sorts of things you can do with this from whatever perspective you'd like to look at it. Over the years, we've worked with a whole range of folks, and people like it, whether it's technical folks or non-technical folks, because you can see what's going on, and that's quite a useful benefit of looking around in 3D with a scan. Kinds of problems we work on would range from a lot of NAPL issues, targeting water supply for people, doing geotechnical issues to keep people's rigs from falling over and things like that. And then we're not limited to where you can take an image. So we work across cities, we work through industrial plants, we work through rail yards and things like that. Well, we can go over the water. It's any place that you can get to, we basically can collect data sets. And, we're looking at an image here, and we're going across the street and collecting data set here. People like to think about this, oh, you guys do geophysics. No, we do electrical hydrogeology because we're collecting a data set using geophysics, and we're doing that with QA/QC protocols. But it's similar to saying, I'm collecting a benzene sample out of a well. oh, so you're doing chemistry. No, the chemistry's done. We're doing environmental work to figure out what the site's doing relative to benzene concentrations. So the processes we've developed, we're not playing with knobs and changing things. We're collecting samples and seeing what's happening in the subsurface. We just happen to be doing that electrically instead of using a well somewhere. And this kind of site, whether it's Cape Cod or Borden, these sites from the late 80s, early 90s, um, they gave us some great lessons, and the lesson was monitoring well is great for pulling fluids and telling what's happening at a location. It's not a characterization well, but even in a simple geology like Borden or Cape Cod, you don't understand what's happening by poking in wells, and you'd have to get so many wells that it's not a really useful approach. Um, unless you had a lot of freshmen to go out and sample these wells all the time, you're not going to get a lot of information in an effective way. And then the other thing we found over the years is that, the simple sites that we teach in basic hydro of nice single source, single pathways, or homogeneous isotropic geology, those things really don't exist. Our contaminated sites have multiple sources, different things going on, and then unknown histories. And then you're putting that into porous media combinations with fractured rock and then other things going on. So we don't get to enjoy simple things. And so taking the approach of we'll put in 3 more wells, that's not going to help anybody in most of the sites we work on. So if you look at the other industries, they do the same thing, whether that's small objects like your knees or big objects like an oil field. They scan and then they go in with their invasive work. Most people think of the scan like the guy on the left, that a scan is something that immediately tells you what's wrong. This guy went to the dentist because he had a sore in the roof of his mouth. The dentist says, I'm not the person for you. But people think about scanning being, oh yeah, you just look at the scan and you know what's happening. Most of the scans that people do medically, you have to have somebody interpreting it and making good decisions about what the scan means. Same thing for the oil industry, but the funny wiggles you get in the oil industry, people aren't usually expecting that to tell you the answer immediately. They're expecting you to work through the data. But for a lot of scans, people want it to just pop out and tell you exactly what's wrong, which for the guy on the left, that's easy enough. But if you have questions about whether his second molar has got problems, you probably need a little more experience. So there's different scan targets that are easy, other ones that are more difficult. But both of those approaches, whether it's medical or oil, they add cost to what you're doing. And taking the picture of his skull did not actually fix him. It just added cost, but it provided really good data about what to do next. And the oil industry, they were really hesitant to do 3D seismic because, well, that adds costs. And that difference between they were hitting their targets about 30% of the time and switching that to 80 to 90% of the time, having your targets hit, that gap between certainty was where people decided, yeah, we're gonna spend the money in advance so that we know where we're going and what we're doing next. Back in the 20s, people were complaining about this because the folks doing dowsing were winning in terms of getting people to look at oil fields. So in the 20s, they started trying to do this. They were getting frustrated. In the 1970s is when the oil industry actually adopted this more completely. So it takes a while for an industry to switch over. Environmental's no different. But there's folks like the ITRC, and they say, hey, what way should we do these things? And should we characterize and figure out your patient has a problem? They have a problem with the knee. They have a problem somewhere in their abdomen. Okay, we have a problem. Let's just open them up and start looking around. And the medical industry said, yeah, that's probably not the best idea. Maybe we'll take a scan and target this a bit more. Same thing the environmental industry is discovering is that if you spent some money to do remedial design characterization and look around because you know you're going to spend money on remediation, instead of dumping money into remediation and saying, well, that didn't work, let's dump some more money into another remediation, that if you characterized it well, that the remediation you do would be more effective and take less time, and you'd save a bunch of money, either in the cost or in the time or in both. So the electrical hydrogeology is a scan first process where you get that certainty in the next steps so that you can go forward and be able to do things effectively. So if we think about that for a basic gas station, um, over the years of studying this stuff, we found that the gasoline does not sit like some sort of nice pancake. It's not in a homogeneous isotropic setting. And so, poking a couple holes and then cleaning stuff out, you very, very commonly miss things. And we normally get called after people have tried a couple of remediation and they still have things that don't make sense and they're missing things. So we put stakes in the ground, connect that with a cable, or we can install that in the subsurface and monitor the same way you would install a well instead of just taking a geoprobe boring. But we'll get a set of data, we can look through the subsurface and then go target things. And that would target channels or fractures or secondary sources that people didn't know about. But it also tells us about the bioactivity of the subsurface. So we can look at if things are decaying and how things are working down there so that you can make good decisions. So that's the basic approach is we're going to scan first and know these things versus just trying to poke wells. But we can then go in very, very targeted, go in and clean out those locations and be able to walk away. And that's the useful part about it is seeing the effectiveness of being able to do this approach. Now, how did that all work? When we started out, we were trying different methods and we tried subsurface approaches with wells. We tried surface approaches. We tried different kinds of geophysics. And it was, okay, what kind of problem do we have to solve? And a lot of problems we have in the environment is to see dark things. And so if electrically, we're going to look around, we're going to look for resistors. So you're going to look for NAPLs, which whether it's a fuel or a solvent, those are electrical resistors that you're pouring into the ground. So it's making it electrically dark. If you're looking for a nice sand channel, that's the dark part. It's the part that's less more resistive than the areas around it. And so you need a tool that sees in the dark. And so that's why a lot of electrical methods weren't particularly effective. And we went out with electrical methods and got things like the stuff on the left, and either targets didn't show up or they're in the wrong location of the image. And it was because you're asking the photographic method, what's the dark part look like? So we had to work on figuring out how to do that well and create the camera that looks around in the dark. And so we ended up increasing the sensitivity of the method by about an order of magnitude and then being able to target things. And this is an image that John Wilson from EPA and the National Groundwater Lab took a geoprobe and poked the death out of it because he said, I don't think NAPL is going to sit in these little blobs like that. And after poking it and taking lots and lots of samples through that domain, yeah, okay, it does look like that. And so we see that on most of our sites is that the materials, the saturation of different NAPL bodies are sitting into sort of discrete chunks. And so if you're mediating as if it's some sort of homogeneous area, you're spending a lot of money that's not really going into effective things, and you're probably missing chunks that are going to cause you problems later on. So that was the switch we made, and so we stopped working in the subsurface with our tools. We go from the top and look down, and this is the reason that all can happen. In terms of when you take a picture, when you look at a contaminated site isotopically, you go, well, I'm not looking at benzene, I'm not looking at solvents, I'm not looking at water supply, I'm looking at isotopes. Well, what does that mean, and what does the number coming back mean for what I'm trying to do? Similar sort of thing with electrical pictures is we're taking a picture, and it means stuff if you have been reading these for a while, and I've been reading these for 25 years. So when you're reading these things for a contaminated site, what does it mean and what do you do next? And so you got to get a little bit good at reading these sometimes. But there are signals in there. The geology's there. If you clean off all the contaminants and things, you could take nice pictures of channels or fractures or faults and look at them electrically. And so, for example, a fault, when a rock breaks, it gets more conductive. And so you can see the strike and dip of the fault if you've got enough images to catch the angles. Otherwise, if you got a single image with a fault, you've got apparent dip issues. So you've got to think about two-dimensional imagery and what the geology you're trying to look at. Are you orthogonal to a channel, or are you running along a channel? And what does that picture look like? The groundwater, if it's homogeneous, it just makes it more conductive. If you've got saline issues, it makes it nice and conductive. If you then do contamination and put some nice electrical resistors like solvents and fuels, that makes it nice and dark and resistive. And then biological activity is the most conductive thing to deal with, and that's what we call the mold in the subsurface. and it basically gets kind of moldy and gets really conductive. So let's look down 500 feet. So you got a nice flat property. These things are really good to work on with clients that are really, really good to work with. And, our client in this case was great at going, hey, I got a problem and we want to try this, but it's way down there and we're not sure about things. So they were ready to try things and look around, and that worked out really well. We saved them about $20 million looking around about 500 foot down at an elm apple plume. But at the top, you go, okay, well, we think it might be in some channels down there. Well, where are they? And so, where you're going to stick an oil rig, or a drilling rig, is going to be a bit tricky. In this case, we've got an image here, and it's looking down 500 feet. Cooler colors are the conductive, and warmer colors are the resistive. And so we end up with this resistor that comes down here, and we're looking at, we knew about where the water table should be. And we get this area that nothing much is going on, and then there's nothing there. And then this area where we've got this resistive body, and we ended up with sands and gravels and things, but we also ended up with 5 foot of elm apple. Off to the side of it, really conductive things. And this would be the mold growing around there. So there's some bioactivity happening around there. When you have a fresh spill, it'll just be the resistor. As bioactivity gets going, you'll get conductors going around there. And so thinking about what to target and what you have is part of reading those images. But when you then work this out, poking a hole to 500 feet with a rig, that's like $150,000 per hole. And finding channels is not going to go easily. So this instead says, here's your targets. And this was giving them the paleo channel locations. They can then look at putting in the down gradient sentinel monitoring wells so that the regulators were happy that things were being well watched. And then we had really good input to be able to put it into a groundwater model to test various options for remediation and management of this system. So a standard sort of approach, you would have some notions about elm apple pathways, but mostly your notion would be that they're hard to find. And then for decision making, you'd go, well, I don't know if we missed something, but with the imagery, you go, okay, we're pretty sure we found the things we're looking for. So you could spend the money really quickly if you say, hey, we're going to drill 10,000 holes. Well, that's a really big bill. And so you're probably not going to drill enough to have much certainty. But for a couple of holes worth of money, you can take images at the top and be able to get that certainty. So we got the subsurface scanning providing the targets. We use that for groundwater modeling to do the higher data density and be able to see what the different options were for the site. And then the management team, they're working with us, and what you need is people that are going, okay, you guys are geeky and look at electrical pictures, but I need to manage this issue. The chats back and forth through the data sets, working with a good team is really useful to say, okay, these are your options and this is the different ways you can go. And having those conversations is quite useful versus saying, hey, we know everything or you know everything. We're integrating as a team is where it's really, really useful. And that was a great team to work on for the site. Let's dump some diesel in karst. So this is a municipal water supply well in Oklahoma. All the wells got to be non-detect in 2 years in a karst setting, which is not usual for this sort of thing. Water table's about 100 feet down. So taking the scans, looking around, there's not a lot else going around out here, but if you can't clean it up, this thing's going to be a problem for a really long time because it's fractured and karstic dolomite. So if we look at what we got on one of the scans, this was the tank that leaked out, 2,000 gallons of diesel. This was the excavation pit. And then if we look at the electrical data, right below it, we have a big resistive body that shows up. And you go, okay, well, you dumped in liquid resistor. You have a big resistor right under where you excavated. I'm going to guess you have some diesel left behind. And so that would be a target that you'd go after. You have this conductor sitting off the side, and we know that bioactivity makes things more conductive. So you go, well, did it run down into this dolomite and get this colony growing to the side? We probably should drill into that. And then we have the water well with the casing that's not particularly deep. And then we know that that's impacted down at 100 foot down with diesel floating on the water table. So we do have some intermediate range things that we can think about. What does that mean? So we could drill that and we find the conductor actually is just weathered bedrock. Um, this intermediate, some dissolve phase, and then you get free product in this nice big resistor. So we can then go target things better, and we did things like back trucking it out of there, and then we followed it up with some surfactant flush work, which normally in a karst setting you're going, I don't know about putting surfactant in there and getting the stuff just to move around, but we had such constraint over it that we felt confident doing that. So we ended up with a CSM of a nice diesel source zone and a diesel flow path down in the supply well, and then epikarst and a soil zone. And you can build out these conceptual models in 2 and 3D and think about what to do with it and then make your decisions next. We also had to get this through the regulatory community, and they really appreciated that our steps were very clear in what the data was happening next and what the decision making was. They weren't going, I don't know, maybe you need 3 more wells. And a lot of times the regulators, the data is not certain enough and they're wanting more certainty. And so the imagery did very well for helping the regulators with that. And so then you have a guided remedial design, and we did work at a perched water table up here, and then we did a work at the water table at 100 feet. But we can also monitor. And so you can either do this by sampling a couple different times, or you can install a cable at the surface like you're installing a phone line. And it's the same thing as thinking about installing a monitoring well. I could geoprobe down and I could sample one time, or I could put in a chunk of PVC and grab water levels or water chemistry whenever I want. And so putting a cable in the top, you could take a picture whenever you wanted. And in this case, instead of looking at whether things are more conductive or more resistive, we're looking at where they changed. And we got a lot more conductive in this area around the pit was filled in with gravel after it was excavated. So we got all this conductive stuff started, and you could see the CO2 coming out of the wells and things like that. But basically, the remnants of where this stuff flowed showed up because the bacteria started lighting it up. And so you knew that the bacteria were growing, but you also knew that they were in the paths where things were at. And so it gave you some confirmation of the conceptual model, but also allowed you to monitor it. And these wells ended up non-detect in under 2 years. So 2 years later, you've spilled 2,000 gallons of diesel, and a lot of projects people are starting to characterize with wells and figuring out the karst is pretty messy. We were done after 2 years, or less than that. Much fewer wells, and the temporal image and trying to do that approach gave us a really good understanding that we were effective in our conceptual model and our remediation. So we didn't use it a lot for watching where the remedial products went, but you can do it that way. But we used it to watch and see things that were good. And the president of the Ada Water Resources Board at the time was also a former member of the EPA Groundwater Lab. So ends up being a PhD in charge of their Water Resources Board that understands impacts and things, and really liked the use of this in terms of getting to a solution. If we think about monitoring, so I said you can install a cable. You can also just put stakes in the ground that you can come back to and have monitoring points. And what you're doing is trying to make the noise level for the difference in the images as low as possible. And so we do this on research side and on a commercial basis in different locations for different problems. Here we're looking at one of the NREX segmented horizontal wells. And that's going down through a DNAPL plume in bedrock. And then we've got images going on either side of that to be able to watch where did the injection go and different issues with that, and do we need to make adjustments in where the injections are going into this well or segmented well that has a bunch of different ports. When you do that, so we can install electrodes or we can just trench in. So this is the research side, and we've trenched in a kilometer-long cable. And so that's sitting out, and right now we're getting a ton of rain in Ada, Oklahoma, and we're monitoring a kilometer-long cable down to 200 meters, and we're watching recharge happen in a karst system. So, this could be a shorter cable monitoring a shallow plume, but if you want to look down to 650 foot or deeper, you can just put in a longer cable. It's a 5-to-1 ratio. So in terms of doing that, it makes it that you have less people having to go back to do the monitoring. And we're working on getting a setup where, somebody could go out and collect a sample for us, versus having us send people out. And it's very similar to saying, I'm going to send somebody out to collect a water sample for me. We can have somebody go out and collect a picture for us. They would just plug in at the box and collect their picture. So for this one, we would go in and hook up and take a picture before and after injection. When we'd have these different injection locations and they had a couple different compounds going in. They throw in about 1,000 gallons in each one of them, and we can then see where it went and what happened. So got a couple of interesting things. One is the water table is brackish in this location. So when you injected, you actually made it more resistive. You made it darker. And so instead of being a conductive injectate, which most people think about, we're injecting into a brackish groundwater, so we're making resistors show up, except for in this spot. And we had this weird zone showing up. So they drilled it. And that's one of the benefits of having the scans. You can go in and test your patient out and see what's going on. And when they did, they said, yeah, that was like the strangest zone we've had in this entire site. And it was full of fluid and fractures. But otherwise, their injections did normal things except for this guy over here. And there was something to do with this zone that injectates went and basically squirted all over here. And there was some questions about the well construction. There's questions about the geology, but we know that was a weird area. Injections over here, they weren't as strong signal-wise, but they're also much lower hydraulic conductivity. And these gray guys are where the fracture zones were, and they were syncing things up relative to those, and those were determined from the initial scans that we collected. But you can slice and dice this, and so this is slicing going from about 10 feet down, 15 feet down. Then we get into the well zone, and then we are looking at the well zone and the phreatic zone and looking at as you're going down below. And we could see that when it got up in the vadose zone, it got more conductive because you took a dry vadose zone and made it wetter. And then in the phreatic zone with the brackish groundwater, it made it more resistive. But you can see these fracture zones sort of controlling where a lot of the injectate went. And so they could see that, yep, our understanding of where these fractures are at is pretty good. We know the injection by having the segmented well, we know which ones really got hit. And then they went in and by looking at the well data combined with this data, they said, okay, we want to hit these ports again. And so they could do some polishing on the injection by just hitting the ports that they wanted to clean the fracture that was still the more impacted fracture and dealing with that. We also see surfacing. And when we first started doing this, people weren't really happy because they said, we were hoping that you would show us the stuff injected laterally and happily into our zone that we've characterized. And we go, well, it did, but it also shot up and it shot down. And we see that on most of our injections, that stuff squirts. And so as long as we tell people that ahead of time, they're not sort of traumatized by the image showing that things weren't homogeneous, isotropic, and friendly, that things sort of squirt when you inject things in the subsurface. But seeing what was going on, knowing where your ports are at, you can go in and remedy, and that's what they did on this site. So in terms of doing this, you can either really drop down the amount of time you're working on things and look at which tools you could apply instead of drilling another 3 wells and hoping things go well. And then also reduce the amount of money you're spending because you're going to go target particular locations. And so your treatment volumes can go way down. Sometimes your treatment areas go up because you find a new spot that you didn't know that they dump stuff out the back door too. So you're going to have to deal with reality that happens. But when you go to remediate it, you're actually going to the spots of interest versus trying to hope that you'll get close to it. So in terms of how we work, we give these environmental educational conferences and webinars. And then we've got like ways to work where we translate what you know about your site into the way a electrical photographer would think about taking pictures. And then work through ways to image the site effectively and go forward with the process. So, Mike, I'll turn it over back to you.
All right, thank you very much. So if you have any questions for Todd, you can go ahead and start dropping those into the Q&A button down on your screen, and I'm going to go transition over to my presentation. Can you see that, Todd?
I cannot yet.
It is coming through on my end.
Do you see it now?
I do now.
Oh, you do now. Okay, great. All right. Thank you. Okay, so we're going to transition this a little bit. So, Todd gave us, it's a great tool to, create or, create these, qualitative images. So AST, so we're a remediation contractor. We help consultants develop remedial designs. And so we'll kind of tell how we take those sorts of data sets that like Aestus, or we'll talk about some others like MIP and UVOS and those sorts of tools, and how we take that and then we transition that and be able to get quantitative data sets to be able to make decisions on remedial technologies, combined remedies, and those sorts of things. So as I mentioned in the beginning, Mike Mazzarese, I'm a senior engineer with AST, based in the Denver area. So, I've been putting things into the subsurface, reagents into the subsurface, pretty much since I got out of graduate school. So, 24 years ago now, and we don't all of us that have put a liquid or put a slurry into the subsurface, none of us are, batting 1,000, right? And so why do sites fail? And I think there can be multiple reasons. I think two of the larger reasons are um, you know not understanding exactly where the contaminant mass is, and then contact, which is actually now getting your reagent in contact with that contaminant mass, isn't a focus for this presentation. We've got others that are in our webinar library if you're interested. So we're going to really just focus on the rest of our time on understanding that contaminant mass from from a phase standpoint, so from aqueous, saturated, and also from a speciated standpoint. Those are all really critical variables in coming up with a appropriate remedial design. And I'll come back to this image here, but this is a quantitative 3D image. So this is using soil sampling, and I'll actually circle back to this here in a minute. So we've got different levels of characterization, right? And so this first one is just our nature and extent. So this is going out and doing that initial survey, soil, groundwater, vapor, trying to figure out what the extent of the plume is, right? Source area or the plume. This is not really, this isn't ideal for us as remedial design practitioners to be able to come up with a design, because usually it's too lean of a data set. Usually limited on saturated soil. Maybe the monitoring wells are, too far apart. So it helps us develop, FS level, here are the potential remedies. But when it gets down to it, of us having us to develop a remedial strategy, usually not dense enough. And so we can use things like high-res site characterization, or HRSC tools. So things like the MIP, the membrane interface probe, which is usually teamed with the HPT, the hydraulic profiling tool. You also get electrical conductivity. You've got tools like the OIP or the UVOS. But what's important to note is that these are qualitative. This is all qualitative data. We're getting an electrical response, right? We're getting PID, FID, XSD, ECD type data. So it helps us to define the box. But when I say we need to understand limitations, I can't take a PID, a PID response, a 10 to the 6th on the PID at 20 feet BGS, and be able to translate that into a remedial design, because it's not quantitative. So it helps us understand where it is, and a little bit about this, the hydraulic conductivity changes using things like the HPT, grain size using the electrical conductivity, but it really doesn't help us transition that to remedial design. So The RDC, or remedial design characterization, um, is something that we've been using for 20 years, to where we're taking spatially and vertically dense soil and groundwater samples. And I'll go ahead and I've got a separate slide broken out for that. I'll go into that a little bit more. And more recently, now we're taking all this data that we've collected and now putting that into 3D models. And the key word there that I bolded is these are quantitative models. Now you can layer in your qualitative data sets like MIP, like UVOST, but the key is that Q stands for quantitative. So that's this image that I showed before. This is a quantitative 3D model. And this video here that I'll show, this is from a site. Actually, if you got the newsletter that I put out a few weeks back, this site was highlighted, and this was a tanker spill on the side of the road that you see there running north-south. And you can see our injection points. This was a series of PRBs with some hotspot injections as well. But the nice thing is, once these models are created, you can take this to the field, you can layer in your injection program, and then you can quarterly dump in your monitoring data and be able to update the model and create these nice videos, which are really important, I think, whenever you're trying to transfer this data to stakeholders, right? And I don't have the most current data here. This goes up through Q1 25 now, and the site, this particular site, has been no further action has been requested. So an RDC from AST standpoint, again, this is really understanding spatial and vertical distribution of your contaminant mass. And this is really critical for source areas, right? So, plume, when you're talking about a distal end of a plume, low concentrations, a lot of that's, I would say in general, a lot of that is going to be in the aqueous phase, with a less of the percentage of the total mass in the saturated phase. But in a source area, that's all inverted, right? So we've got the bulk of the mass is going to be in the saturated soil typically, or in the unsaturated as well. And so we work with our consultant partners. You all know the sites better than we do. And so we sit down at the table and look at the site, all the data you have, and then develop this high density sampling program. To give you an idea of what that looks like, this is a carbon tetrachloride site that was in the Pacific Northwest. And we had 10 soil borings in a rough grid pattern and collected 90 soil samples in one day. And I'll get to it in a little bit, how we make that cost effective, because I know that sounds like a lot of soil samples, how we make that cost effective for our clients. And so when I say dense, what do I mean? I would say in general, we're sampling every 1 to 2 feet vertically, usually on a 2-foot interval. And then if we've got anything, if we've got any distinct lithological changes or PID hits, say, in between those 2-foot intervals, we'll go ahead and grab an extra sample. If you've got that long monitoring well screen where you've got a 20-foot, saturated column, obviously that really does help us understand vertically where the mass is. So you can always break that up and grab temporary groundwater samples as well, vertically with depth. That's important for a source area, but also, again, in that distal end situation where you're looking at, putting something like a permeable reactive barrier in, really understanding how that mass varies laterally, but also vertically as well. And this whole process was recognized in that ITRC guidance document that actually Todd referenced earlier in the presentation. So this site, to go back to this site, this is each of those nodes that you see is a saturated soil sample. And this was a large chlorinated site. And there were over 600 soil samples collected. And our project support laboratory, which is based here in Denver, where I am, runs all of this pro bono. So it's not certified in any particular state, but we're making but it's all standard methods, 8260B, for example, GC mass spec methods to be able to, again, assess groundwater and soil concentrations. The ultimate goal is to optimize the remedial design. And so here's an example of a site where a large RDC was done. This was on a UST site. And each of these sub areas that you see has a different design associated with it. Because especially something like a UST site where there's been typically multiple remedial actions, maybe there was some excavation, some soil vapor extraction, maybe some injection of, in the past. And so the data is usually all over the place. And so getting a nice fresh snapshot, we're not relying on soil data that's 20 years old. Get a nice current snapshot of where the mass is, and then now we can really kind of surgically attack each of these injection zones. So your injectate concentration is going to vary between the different areas, but it can also vary vertically as well within these areas. And I would say on most sites, the cost of doing that additional upfront sampling work is going to pay for itself in just that optimization process, because now we can peel out safety factors and we can really focus our remedial efforts. So here's an example of a site that I was involved with in Canada where a few injections, 3 different injections were performed. There really wasn't a good handle on the mass. This was a PRB installation, down gradient of a pretty close to where the former USTs were. So there was a significant amount of saturated soil mass that really wasn't accounted for in the original designs. So you can see here, you got your BTEX concentrations are really bouncing around, some increases, some decreases, but really inconsistent. And then when you see those 2 vertical black lines, dashed lines, that's where we came out and spent really just one day going out along the length of that PRB, collecting saturated soil and water samples, really identified where the mass was, came out and did, this was a FOS 200 injection. And we can see the data here, and these concentrations we've stayed below 10 parts per billion benzene up until the current samples that have been collected. So the QHRSC, to circle back to that again, so we're taking all that data, whether it's qualitative, quantitative, and we're building this all up into 3D models. And so we can, again, integrate your MIP, your OIP, UVOS type data, and then we're going to put that onto a 3D model and really understand where the unsaturated mass is, where the saturated mass is, and this really helps us understand whether this is going to be, say, a combined remedy. Are we going to do an excavation and seed the excavation, inject below that? Are we going to deploy various remedial amendments? Everything, all the technologies that we work with day in, day out have, they all have a box that they fit into, right? Everything has limits, right? So we want to make sure that we're staying within that box for each technology, and having this kind of information really helps us make those decisions and ultimately help set expectations for remedial time frame. Are we going to have to come back and do a supplemental injection in 2 years, say? And so that really helps our clients set long-term budgets as well. And then also remediation endpoints. We want to be realistic with our endpoints in that, if we're starting off with a really high concentration, depending on the saturated soil mass, or if you've got a significant, say, amount of, LNAPL or petroleum hydrocarbon mass that's, you're in that 2, 3, 4, 5,000 milligram per kilogram range in a source area, it's going to take a long time for that to eventually work its way out of the soil, regardless of what the remedial technology is. So those 3D models, again, really take all the information, your qualitative, quantitative, your lithological data, really helps us display the distribution of contaminants aerially as well as in cross section, understand the hydrogeological framework of the site. And so here's just a couple of notes on HRSC again. So, MIP is it is qualitative. And I get data sets often where I get, some old soil groundwater samples with a current MIP report, or maybe they came and they, did a few, what I would quote unquote confirmation samples, and am tasked with coming up with a remedial strategy, and really can't make those decisions because, again, you're dealing with an electrical response. And even if you talk to GeoProbe or you look at, ITRC documentation, you know, it makes correlation problematic because, again, it doesn't discern between phase or, compound. And then we can ultimately integrate our remedial design as well. And so here's an image of that, where this is the 3D modeling software that was developed by our partner company in Denmark, is what we use in the field. And so we can drop our points in real time as they're being completed in the field. And as you see the different color codings, these are all different loadings. So we see our, blue and purple points, that's our source area. And then we've got our yellow points that are circling that. That's more of your, plume focused injections. So I think we have time. I'll try and get through these really quickly so we can open this up for Q&A. So this is a UST site where we went out, and you see we have our monitoring wells are all the blue circles, and the soil borings that you see, those are our RDC locations. And so this is TVPH in soil. So we can see we have two distinct hot spots there. So that's in milligrams per kilogram. So we're looking at, the red is, starts at about 3,400, goes up to about 4,000 milligrams per kilogram. So in that range that I was talking about, you're talking about whether it's measurable NAPL or you're definitely above CSAT for sure, right? Here's your benzene in soil. So this is interesting, right? So we can see here, depending on the remedial technology that you're using, so something like activated carbon, obviously understanding, based on sorption isotherms, different compounds are going to sorb differently. So understanding distribution of the specific contaminants is really important. So TVPH is good to understand the total mass, but we also need to understand, and benzene is usually the driver for cleanup, right? So understanding that in soil, which is going to ultimately, feed groundwater, which is the third image here. And so this is our benzene in groundwater. This is in milligrams per liter. So in those hot spots, we're in a 10 to 12 milligram per liter range. So here we are looking at it in a couple different cross sections. And so this is really where the optimization, I think, really kind of comes in, because in general, we've got a good handle on the aerial extent based on the existing monitoring well network. But really where I think the optimization occurs is in when you're looking at it in profile. So now we can really, again, vary our reagent loading with depth. So when we're in these blue kind of cooler zones, we can come in with a lower dose, and then where we have those red and orange areas that you see in the profile, we can come in with a much higher dosage, and to be able to really optimize our remedial design. Okay, so this is actually that site that I just showed. So these are all the injection points that were ultimately laid out. So again, this is all integrated into the 3D model now. So our field crews go out, and all this is preloaded onto their tablets. And so as they complete each injection point, all the information that we track is going to be logged, right? So your flow rates, pressures, did you have any daylighting? Do you have any issues? All those notes go in for each of these injection points, and this is what ultimately goes to our clients as part of the injection report. So I think I'll wrap up with this here, and then we can go ahead and again open it up for questions. But this just compares the preliminary versus the final design, and for this particular site, to where you could see our preliminary design, which is based on the monitoring well data and the existing limited saturated soil data that was available. And on the right, we see all these different color coded areas. Again, each has its own design associated with it. Again, based on the 3D images that were that were created. And this site is we did an injection, I guess, going back about 7 years ago now. And so you can see we've as of 2022 we've significantly shrunk the plume. You see this the area here has been complete. We've knocked these concentrations in groundwater down significantly pre and post. So now we're down into this this lower range here. We're looking at 1 to 2 milligrams per liter of benzene, but starting at very elevated concentrations. And on a site like this where we go in and we know we have those 4,000 to 5,000 milligram per kilogram concentrations in saturated soil, really helps us set expectations for our client, because we know this is going to be a long-term project. And so for a site like this, if the ultimate goals are, say, MCL type criteria or some low concentrations, we can set the expectations that, like, when this remedial technology has run its course in, say, 3 to 5 years, we're going to have to come back and probably do some supplemental work. Maybe if it's in a state that's got more of a risk-based closure program, maybe this is fine. So I'm going to go ahead and skip this last. This is a chlorinated site that we were involved in. A lot of the same data. This site was much larger. It's one of the largest RDCs and injection programs that we've did. But you can see here, this is probably kind of like more on the extreme end of having to break up a site into different treatment areas. And the larger the site, this can definitely happen. But you can see the optimization by just all the sheer number of injection areas that we were able to break out on this site. So thank you for your time. We've got about 7 minutes till we hit the top of the hour. So I'll go ahead and open up the Q&A. Todd, if you want to get unmuted here, we can go ahead and answer some questions for you or for me. So go ahead and drop those in. So I guess, Todd, a couple questions for you. I know, I think one of the obvious ones for a lot of people is when you're working around, utilities or structures. How does that influence your data sets?
So we always work with utility maps, and we always do public.
Todd, I can barely hear you for some reason
Oh,
now. There you go.
sorry.
Yeah, you're good. You're good.
There we go. So we work with public and private utility locates before we go out, make sure that we don't hit anything. And then detection-wise, most utilities in the modern day aren't really well detected by this technique. So that's actually useful for us, because we're not doing this on a utility location basis. But all the coatings they put on pipes and things now make them pretty electrically isolated. So for most of our sites, it's maybe a site every 3 years we actually find something that's interfering with an image. So the only thing that really interferes with us getting a good data set now is if you have a transformer yard that has a grounding grid where the entire ground surface is basically mesh. That's the only time we have any particular interference issues of getting good data sets to work with.
And what about depth limitations?
So we're a 5-to-1 ratio. So, working down to 1,000 foot, we're at a mile worth of cable. And so we can go deeper than that if you got problems down there. But most of the things we work at people are working at problems that are somewhere between 30 and 300 feet. And so those are easy enough. And going either through buildings or across roads or going different places, up hills and down across waterways. We've worked out all that engineering over the past couple decades. So it's just, where do you want to collect, and do we have land access to a particular location?
Well, I guess not literally, but the one of the $1 million questions we always get is, and I'm assuming that this is for you, is Could you give us an idea of the cost of the service based on, one of the examples that you provided?
Sure. So that's the social side of doing this is people want to know, like so when you go to the doctor and they say you want to do an MRI, well, there's a way to pay for that, right? And so it's not, hey, do I have to find $5,000 right now to pay for my MRI? So the cultural side has to take a time to catch up in the scanning. Um, so if you're doing monitoring, then your install of a cable to monitor is going to be same sort of cost as I'm going to decide to install a well.
Mhm.
Um, so instead of paying for well parts and drilling, you're paying for a trencher and a cable.
Mhm.
So those things are very similar. In terms of doing it from the hey, come out, collect images, analyze it, put it in 3D, do all the integration. That's a couple 100,000 kind of project.
Mhm.
And so it's how does the cost go? Now, if you said, hey, go out, put a bunch of wells in, sample them, analyze them, look at their trends, and then come back to me, it'd be a similar price for characterization. But usually the wells are people do a couple at a time, right? And they split
Mhm.
the costs out and things. So we've been looking at how to deal with the social side, both with doing things on a monitoring basis, which changes the cost structure, and then also looking at ways that people could rent systems that could take the kinds of images we collect.
Mhm.
And so trying to figure out how to make it so that you can change the cost structure to be parallel to things people do with wells. But
Mhm.
for, a dry cleaner or a chemical plant or a gas station, it's not something that's a $10,000 thing. It's in that 100,000 kind of range. So
Mhm.
it's okay. How do we make that more palatable to people? But it's the same problem that the oil industry had to overcome with where to put the scanning costs, and the
Mhm.
medical industry had to think about how do you manage the scanning costs. But they both found ways to manage it because the data is so valuable.
Mhm. Right. 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 Well, what about another question? So what about buildings? So I'm working, say, inside buildings. Is that an option?
Yes. So if you want to go through a building, and we've got a lot of places where you got that solvent source was sitting inside the
Mhm.
building, and you're wanting to see things. So you can go through doors and go through windows and things like that. Your cable doesn't have to be stretched taut. You can take excess cable running around through a door or a window and then come back to a line and hook onto an electrode. Or we've also worked in plants where you just drill through the walls, and you're putting
Mhm.
in a couple inch hole and then
Mhm.
patching that up at the end. And so
Mhm.
we've done several industrial facilities where you're like, well, you could bring a drill rig in there, or all you have to do is get a wire through the
Right.
wall.
Right.
And
Right.
they go,
Right.
I'll take the wire through the wall because that's a lot easier than that drill rig sitting in that plant floor.
Mhm. For sure. For sure.
And we can do that. Like we've had active food plants, active industrial facilities, and they can keep operating while we're working because we're just stretching lines and you
Mhm.
know dealing with tripping hazards versus dealing with shutting things down to get the rig in there.
Okay. Excellent. Well, we're up against the hour here. Todd, thank you so much uh, for presenting today, and I will follow up with everyone with an email that's got Todd's information, and we can also I'll also include a link to the project evaluation sheet that I think you referenced before, and I can go ahead and include one from AST as well. So again, thank you everyone for attending. Thank you, Todd, again, and enjoy the rest of your day.